So I've been working on building Linux kernel with LTO, specifically on battle handling of top-level assembly. Previous attempt to build kernel with LTO had a major issue that it needed at many places to mark functions, symbols in general, with external visible attributes. So that it's not compatible, because GCC's LTO breaks some assumptions made by the kernel. Specifically, global symbols may be optimized away, and symbols can be renamed, and that is done to prevent miscompiling, because we can optimize global symbols, and if we would accidentally call that function, if it wasn't renamed, we would get miscompilation. And similarly, when we globalize local symbols, so we can shuffle them into different translation unit, different partition, we could have similar problems with name conflicts. So the main problem that we needed to handle was top-level assembly. When we export, for example, when the kernel exports some symbols, it uses this assembly, this top-level assembly, and GCC currently doesn't know what its contents actually are. It's just some string, and we do not have any. We do not know that this top-level assembly refers to functions CPU uses features. So for that, we have essentially two solutions. One that currently works, and that is in the mailing list, are heuristics that essentially just go through the entire string and see anything that looks like an identifier. If it finds an identifier, it tries to see whether there is function with that name, and if there is, it marks it so we don't do some optimization, some additional LTO optimizations that might be incorrect. So that would cause it to be renamed, or so essentially the main thing that we guarantee with that is that the symbols are not renamed, that they still exist if they are referenced from assembly, and that is additional. We then also have to handle name conflicts. If you have two static symbols that have the same name, since we can't rename them if they are both referenced from assembly, we need to take care so that they don't end up in the same translation unit, the same partition in the LTO. This solution covers most use cases, so it's I'll continue for the second. The second solution is extended top-level assembly, which we like we have for the normal extended assembly. In GCC 15, we now have support for the extended top-level assembly, so we can mark the individual top-level assembly what it actually uses. Though that's currently not supported by LTO, but I have some work in progress patches that are able to enable it. So this approach is a bit more accurate. We can express any required symbols, which we will see on the next slide. And it's more flexible for GCC, because normally GCC likes to rename all this a lot of those symbols, so we can easily optimize them. But as we will see also on the next slide, that's at least in the Linux kernel, we probably will want to keep the same name, so we will use the similar approach as the heuristics. We just will take the information from the extended top-level assembly. Though the main problem with the extended top-level assembly is that previously we had to mark a lot of symbols with visible. Now we would have to mark a lot of top-level assembly. There are not that many. There are maybe 40, 50, but it's still more work than using heuristics. So probably we'll end up with extended top-level assembly that is preferred for GCC, but we might have the heuristics which actually are not are essentially addition of 40 lines of code. So it's probably not a problem. So in any case, we will have some solution for the top-level assembly. So what do we need outside of top-level assembly? So first off, not everything is actually directly referenced in the top-level assembly. Static call keys are used, even though we actually used we use the name of the function, and then there are some additional information that is this variable with added prefix, and obj tool assumes that exists, that it's that if we are calling that such a function that prefix also exists. So for that we will need to keep the name, and so this is and so far I've been solving it with similar approaches previously, just with visible. So with the heuristics and that this individual visible, this is enough to build the kernel without modules for now. And everything that is needed is in the patches that are in the mailing list. So what about the modules? Previously, I've been skipping this macro, which is actually in a lot of ways what we need. That macro essentially, the intention is that it guarantees that this is the macro in Linux kernel currently used for some things that is supposed to guarantee that the symbol exists, and that the intention is also that it isn't renamed, which unfortunately isn't true for GCC. And this is used in few places for modules, and actually the static call keys prefixes they are also marked with this. And it's from what I can tell, it's used for in few cases for Clang LTO that already is. So the main problem with this macro is that it's used both outside and inside of functions, and I don't think we have a way how to actually express that, how to add attribute to some arbitrary symbol from afar. That essentially what we want on GCC side is use this macro to add attribute that it's used visible, that sim is used visible, and I don't think we have a way to express that if it can be called from both outside and inside the functions. So that if we could do that, that would probably solve many problems with the modules, and we might be able to actually fully compile the kernel. So far we have bootable kernel. I didn't focus on some debug info, etc. And for now it's without modules. Some minor benefits are in the smaller kernels when they are compiled for size. There are 6 or 8%. What I've measured, the 6 was for the default configuration, and 8 was for minimal kernel. And also, one of the benefits is that it actually uncovered several GCC bugs around weak symbols and partitioning. So that's for this short talk. And if you have any questions, yeah. Okay. Okay.
Yeah, hello. So a question about inline assembly. I'm sure, like for Clang, the inline assembly blocks are also like blobs, just portion of text. And why does Clang doesn't have this problem with identifying symbols?
If I understand it correctly, the first thing is that it either the fin LTO compass essentially one-to-one our equivalent, that it keeps the compilations unit together and just move. And the second thing, I think Clang doesn't rename those symbols. So that's one of the main issues. That the Clang mostly focuses on inlining and not actually optimizing the that functions away.
Okay, I see. Yeah. Thank you.
I might be being a little ignorant here, but might a simpler approach to dealing with the problem of symbols being called from outside any function, arranging for call sites outside all functions which can nonetheless contain executable code to appear to be inside a function, so GCC knows these are actually, well, functions. Because fundamentally all these places outside any function which are calling things are actually functions from our perspective. It's just that GCC doesn't know they are.
The problem is that the kernel people are quite resistant to adding too many GCC-specific heuristics for things like this. So,
we don't have the.
oh, okay.
I don't think it's not even a GCC heuristic. It's fundamentally these places outside any function which contain executable code are actually, in a fundamental sense, functions. The problem is that the compiler doesn't know they are. Maybe teaching them that might be a good idea. It doesn't seem to require too much GCC specific. Surely LLVM would rather know that it was inside a function as well.
Yeah, in many cases, those are not actually functions, but are just a way to export those symbols to some outside tool.
Oh, right.
So, yeah, because I gave the patches a go, and thank you for sort of responding quickly, and Andy as well. And it actually went pretty well. It's the static keys in the modules that are the main thing. Like I actually got to the point where I could semi-boot and then AMD GPU crashed. So, yeah, it's
So I understood that you haven't been optimizing inline functions yet, but has there been any preliminary performance benchmarks with just the inlining so far?
I haven't looked at the performance, actually. The comparison of the sizes is very easy, but I've been mostly focusing on the GCC side, whether we can compile it actually or not.
I'm sorry, I missed the beginning of the talk, but looking at the extended ASM syntax, if you're referencing a function, can you just have the address of that function as an input operand, and basically tell GCC that the ASM is referencing that function that way?
Yeah, this is one of the solutions. We have either heuristics or that, and the problem is that it would need to marking of a lot of tuple assembly. There's a lot of tuple assembly, and last time there was the kernel people didn't like that we needed to mark a lot of symbols. So I don't think it would be much better if we needed to mark a lot of tuple assembly.
But I mean, at least that way it tells GCC we're using this.
Yeah.
GCC will know that.
Yeah, that is the preferred solution, but probably not what we will end up with.
It's even more complicated because kernel will, for the next 10 years, need to support also older GCC versions. So you need to macroize it that you add this input argument only for GCC 16 because 15 doesn't have LTO support for this, and inside of the ASM template you also need a different thing to say if it's an operand or if it's a string, but it's doable, and the question is if we can convince the kernel maintainers to take it.
Yeah, concerning the benefits of LTO in kernel, I was showing on previous talk, I was showing the spec numbers, and the performance improvement was like 2%, which is not that much. If you compare things like Clang, the performance improvements is like 20%, which is a lot. And with kernel, I would guess it would be more on the spec size because a lot of inlining and other things are done by hand. But I think it's also kind of a good long-term investment. Like, if we enable the LTO, you don't need to put everything into the headers, and the compiler will do it for you, which I guess might be also good once the Rust becomes more actively used, if GCC gets working Rust, because then you can inline between the programming languages, which you cannot do easily by putting everything into the headers. So I think, it's kind of the pain which needs to be done to get something better later, at least in my mind. Yeah.